Welcome back to the AI Research Roundup. I'm your host, Alex. Today, we're diving into DUET, Dual Clustering Enhanced Multivariate Time Series Forecasting, a paper published around December 14th, 2024. It tackles multivariate time series forecasting. This is about predicting future values for several related data streams, or, quote, channels, recorded over time. Now, this is tricky because real-world data often shows patterns that change quite a bit over different time periods. These are called heterogeneous temporal patterns. Plus, the links between these data channels can be really complex. DUET introduces a framework using dual clustering, one part to group similar time patterns and another to understand channel relationships for better forecasts. So DUET uses this dual clustering idea to improve predictions. And if you're interested in seeing how it's all put together, the authors have actually made their code available. They've shared the official PyTorch implementation on GitHub. In that repository, you'll find all the necessary code, including scripts to reproduce their forecasting results and clear instructions to get it running. It's a great resource if you want to explore the practical side of this research. Alright, so to really get why this dual clustering is a big deal, let's look at Figure 1. This figure shows us a classic example of what's called a non-stationary time series. Essentially, non-stationary means that the basic statistical properties of the data, like its average or how spread out the values are, change over time. You can see in the top part of the figure, there's a single line graph representing some value over a long period, but it's divided into three distinct intervals, A, B, and C. Notice how the pattern of the line, its ups and downs, looks quite different in each interval. Below that, we have three separate bar charts, or histograms, labeled P_A, P_B, and P_C. Each histogram shows the distribution of values, so how frequently different values occur, within its corresponding interval A, B, or C. And as you can clearly see, these distributions are not the same. For instance, in interval A, the values are mostly clustered around 0.6 to 0.8, while in interval C, they're more concentrated around 1.0 to 1.2. This change in data distribution over different time periods is exactly what the paper calls a, quote, temporal distribution shift, or TDS. It's these kinds of shifting patterns that make forecasting so challenging, and where DUET's temporal clustering aims to help. Okay, so after seeing the challenges, like shifting temporal patterns, Figure 3 here shows us DUET's actual performance. It's a radar chart, and it pits DUET against several other models on 10 different datasets. The results you see are averaged across different forecasting horizons, meaning how far ahead they're predicting. Performance is measured by mean squared error, or MSE. This essentially tells us how close predictions are to the real values. So, a lower mean squared error is better. And DUET, shown by the red line, generally stays closer to the center of the chart, indicating it often has a lower mean squared error. Okay, so we've seen DUET performs well, and Figure 2 here helps illustrate how it manages the connections between those different data streams, or channels. This figure compares 4 different channel strategies. You can see the channel independent, or CI approach at the top left, where each colored row representing a channel's data is processed in isolation. Next to it, channel dependent, or CD, has all channels interacting. Below, channel hard clustering, or CHC, forms fixed groups, while DUET's own channel soft clustering, or CSC, allows for more flexible, learnable connections, aiming for more targeted information sharing between specific channels. Alright, so after seeing those different channel strategies, Figure 4 lays out DUET's overall architecture, showing how it combines everything. Input data first undergoes instance normalization, making it more uniform. Then, it splits. The temporal clustering module uses a distribution router, then multiple linear base pattern extractors, and an aggregator to combine their findings on shifting temporal patterns. Simultaneously, the channel clustering module uses real fast Fourier transform. That's a technique for looking at data by its frequencies, to learn channel interdependencies and create that selective channel mask matrix. Finally, a fusion module merges these insights before the predictor makes the forecast. Okay, so Figure 4 gave us the big picture, and Figure 5 here really zooms into the mechanics of those key modules. We see the distribution router using encoders, which are specialized neural network parts, to analyze data distributions and pick the right linear pattern extractors. These extractors then perform series decomposition, breaking data into seasonal and trend parts. Next, the learnable distance metric is shown, which measures channel similarity using frequency data. Finally, the fusion module combines these insights using masked multivariate attention, along with layer normalization for stable training and feed-forward layers for more processing to make the prediction. So we've just seen the inner workings of DUET's different modules in Figure 5. Now Table 2 shows us an ablation study. This is where researchers take away key components of their model to see how important each one really is. The table compares the full DUET model with versions missing either its temporal clustering module or its channel clustering module. Performance is measured by mean squared error and also mean absolute error, or MAE, which is another way to gauge prediction accuracy by looking at the average absolute differences, so lower values are better for both. And as you can see, removing either module generally increases these error scores, confirming they both contribute significantly to DUET's accuracy. Okay, so those ablation results really underscore the value of DUET's design. And to show just how broadly applicable this DUET model is, Table 1 here gives us a look at the diverse range of datasets it was tested on. We're seeing data from domains like traffic, electricity, weather, and economics. The table details the frequency of data collection. How often new data points are recorded, from every 5 minutes up to daily, along with the length of each dataset and its dimensions, which means the number of different data streams being tracked simultaneously. This wide variety really helps to show that DUET can tackle many different kinds of real-world forecasting problems. After seeing DUET tackle such a wide array of data, it's clear that its dual clustering strategy, looking at both time patterns and data channel similarities, really boosts forecasting accuracy. This is so important because better predictions in complex systems like traffic or energy can make a huge difference in how we manage them. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll catch you next time.